Okay, so my talk on this PCA 2020 conference is titled Rigid Body Motion Symmetries. The aim of my talk is to explain the abstract, which is posted at the conference website. So let me begin with advertising a recent presentation, which was posted a couple of years ago by David Farrell. Uh, it concerns, as you see, the arithmetic geometric mean, and notably, uh, it states that uh, it, it's being rediscovered in the computer age, and it underlines fast algorithms for computing elliptic integrals and transcendental functions. Now, the reason I'm advertising this presentation is twofold. One of them is obvious. So let me reorder this presentation and present this very last page. Here you see a reference to a paper of mine, the second reference. So I'm referenced in this presentation. And another reason is implicit. This reference is implicit. So let me show you where the implicit reference is. It's here on page 7, where the elliptic integrals of three kinds are defined. And you see here the complete elliptic integral of the third kind appears in studies of rigid body motion. So I think this has much to do with the paper of mine, where I explicitly emphasize the elliptic integral of the third kind indeed in the study of rigid body motion, as I'll make it clear soon. So, of course, the author emphasizes that perhaps the right way to begin with investigating the arithmetic geometric mean is the simple pendulum. And the period of the simple pendulum often is approximated. You see, this is an approximate equality with this so-called small oscillation formula. But of course, one has to wonder, why would we have an approximation? Or what about the exact formula? Well, the exact formula is presented here. It's a complete elliptic integral of the first kind. So here it goes. The author provides several examples to exhibit the abundance of applications for elliptic integrals. And of course, the arithmetic geometric mean algorithm is widely applicable to find efficient solutions for these many problems. Now, this is just an overview. Of course, this issue goes back to May 30, 1799, when Gauss wrote in his diary that a new era in analysis emerges. He was really that excited, and this excitement wasn't really well understood until maybe most recently with the advent of computers, because it was really a remarkable breakthrough which wasn't really well comprehended before the advent of computers. Now, the basic algorithm is presented here. You have two positive numbers. Then the arithmetic mean exceeds the geometric mean. So you have two new numbers, and you can go on with this procedure, which is very swiftly convergent procedure to this common limit. You have this one descending sequence of arithmetic means and an ascending sequence of geometric means converging quadratically to their common limit. So here, just our maybe first prime example is the period of the pendulum. here the exact formula is presented here with this correction of Gauss. So this is now exact formula, and it's fast, and it does not need for the angle of maximum inclination to be small. It can be whatever your heart desires. Now here an example for efficient calculations of this ubiquitous constant pi. Nowadays we have trillions of digits calculated via computers, and the underlying algorithms are those that were founded by Euler and Gauss. Now the natural logarithm function, of course, might be swiftly and efficiently calculated. So here, maybe another example, the perimeter of an ellipse being an elliptic integral of the second kind. The arctan, arcsine, and arccosine. These are examples. Now, so let me summarize that this is from a paper of mine about the elliptic integrals of three kinds. So this is the first formula here. It's the elliptic integral, complete elliptic integral of the first kind, which the formula here is due to Gauss on May 30th, 1799. And of course, it's the founding formula for all calculations for all elliptic integrals of all kinds. So the second kind is here. The numerator exhibits this modified arithmetic geometric mean, which was presented in that paper referenced in the presentation I advertised. The third complete elliptic integral, actually it's the general case. You might view the first and the second as special cases. So you have here the generalized arithmetic geometric mean being here presented as a function of two variables now, or it might be presented as a function of four variables. So now let me skip advertising my own work because this was done for me by some administrator who wrote a note negatively advertising my talk on January 31st, claiming that my scientific views are invalid. So, this is much more valuable than positive advertisement, because, the negative advertising probably would draw more attention. So for this reason, this talk was translated fully into English with comments. So I must thank the translator and the editor for this work, which I much appreciate. So it's actually here the slides are in Russian, but as I said, it's actually there are a combination of Russian and English slides. It's here on Easy Chair, so you might look into these to accompany this presentation. Here the video presentation, and of course it's remarkable for the criticism that that's being presented here, and as I said, translated. So actually, it's quite as you see issue that really brought some attention for some, as you see, quite interesting reasons. One of them, and this is actually quite remarkable, because this is a book that was actually very recently released, 2010, although the author of this book actually died in the uh, previous millennium, so 1993. So this is actually his followers making a new edition, and might even be claiming things not exactly that the author claimed, but they are really quite remarkable for making a conclusion that we cannot have a unifying expression for the motion of the pendulum in oscillatory and rotary regimens. And they're even providing some arguments, topological arguments, trying to justify why this is not possible. Mm. So here you have some formula for the period of the oscillating pendulum, and another formula for the period of the rotating pendulum. Um, mm, uh, Actually, I must stress here at this point that the issue of what one might call analytic continuation of the arithmetic geometric mean is really some remarkable issue that hasn't been really yet investigated. Surprisingly, I must draw attention to two colleagues of mine, Helmut Ruland and Francois Lemarche, who are keeping me posted on their interesting work that I would anticipate be coming in sometime in the near future. Mm. So now let me show you something again quite remarkable because this is perhaps the first text book on physics where an exact formula for the period of the simple pendulum appears. I mean, not until 2013 that David Simpson uh, brought the attention to this formula in a physics textbook. As I said, this formula was really due to Gauss in 1799, but when people ran into this formula, they somehow even didn't really understand its significance, or they have done something that ought not be done with it. I mean, so here, what I mean, you see here the Taylor series expansion. Well, these Taylor series expansion are notorious for their convergence troubles as you approach the boundary. So no matter how many terms you take, no computer would save you from troubles. Mm. However, this formula here that David Simpson, as I said, for the first time presenting in 2013. Now, this is perhaps a later edition of his book. I think it's 2019. I don't know, maybe he has now a newer edition yet. But so here, the formula, this is the formula, the exact formula for the period of the pendulum. And I must pay your attention uh, for not converting this formula to any Taylor series expansion, because this very eloquent and explicit formula is also very swift in converging, and it's not at all concerned with small or large angles. But as I said, of course, there is another issue here, the issue of moving from a pendulum that's oscillating to a pendulum that's rotating. So we have to somehow analytically continue this formula. Uh, so now let me bring your attention to another thing that's again related to the simple pendulum. I don't know, it's really quite remarkable because this is some very basic problem in physics and mechanics. Somehow it's avoided because now see, this is the so-called stable equilibrium of a simple pendulum. So you take this kinetic energy and the potential energy. So when you sum them, this is the Hamiltonian. When you equate it to -1, this would correspond to the pendulum in its lower equilibrium, so-called stable equilibrium position. Now, of course, there is the trivial solution, but then again, that's probably very troublesome to some people who are used to teach this subject for perhaps decades. And of course, it's hard for them to admit that it may not be the only solution to this differential equation. Let me show you what I mean. So here, a family of solutions. So you have this map from time to a point uh, in the complex plane, let's say. So the point is that if you can check this, and if you move this argument, if you translate this argument by some number complex, then you have another solution. So I mean, you have infinite family of solutions, which is parameterized by this shift of the argument. But anyway, so if you check this, then in fact you get a solution to that pendulum in the stable equilibrium, and then this quite remarkable mystery about the pendulum in the stable equilibrium having a period of 2 pi, which is called the small oscillation period, which of course is never the true period whenever the angle is non-zero, because that formula would have to be corrected as we saw with an exact formula. But this small oscillation period, in fact, turns out to be the period for all these solutions. All these solutions have period of 2 pi. So, of course, many would argue that these are solutions in the complex plane, so we really can't make mechanical sense out of them. So they would really viciously at times object to this work as making no sense. Well, let's see if we can agree and skip these solutions. Well, let me tell you right away that we really cannot, and I'll tell you why. So this is the reason why. We have duality for equilibrium. You have the lower equilibrium is being dual to the upper unstable equilibrium of the pendulum. So again, if you take this kinetic energy and the potential energy, and now you equate it to 1, not -1, then you have this unstable equilibrium solution. And that family of solutions that didn't make sense, so to speak, is transformed with this duality. Perhaps pain must be attributed to noting that duality. So this is something is really based on his idea. I don't have time to dwell on that, but take a look at this now map. I mean, you get a point which is on a unit circle. I mean, this is exactly the configuration space of the pendulum. Well, this is the point on the circle squared. Well, square, you'll see it's coming up in a moment. Why is it squared? So this would correspond to a pendulum moving with the exact same energy, which is coinciding with the energy in its unstable equilibrium when it was standing still, so to speak. So with the same energy, it can be moving, and there are actually two motions are possible, clockwise and counterclockwise. And so in fact, we have three solutions. And you might note that we cannot obtain one from another by a phase shift. Well, we have to be careful here. Actually, I mean a phase shift by some real argument, because the issue is quite different if we allow complex arguments. But in a way, you cannot obtain one solution from another by making a real valid phase shift. So in fact, we have a loss of continuity here. Loss of uniqueness of a solution, meaning the same energy, exactly the same energy. There are three solutions, and of course, we cannot allow for any disturbance of that energy, however small. We cannot perturb that, because once we perturb this level of energy, we are no longer in that unstable equilibrium position. This is exactly what we ought not do. So whenever these arguments about giving a small push or doing a slight perturbation is absolutely missing the point. So this is very important, critical solution, uh, and very surprisingly, it's dual to that solution, which we almost were about to omit. Luckily, we did not. So anyway, here, this analytic unifying formula, this is a title of paper of mine, which I aimed with the title itself to refute that statement, which has appeared recently, and I hope it would soon disappear again, because it was somehow rushing to judgment, maybe not giving I mean, after 200 years, people probably were not paying much attention to Gauss' remarkable discovery, missed some important things, so they came up with a false conclusion. So, in fact, of course, we do have an analytic unifying formula of oscillatory and rotary motion of a simple pendulum, and this formula here might be very succinctly described as uh, uh, the Galois essential elliptic function. So this might be viewed as a map, as being an elliptic function. It's a two-variate function. One of the variables is time, and the other variable is that angle, which when it's might be viewed as the angle of maximal inclination of the pendulum. But of course, it doesn't have to be this argument phi doesn't have to be real valued. You might have complex argument here, so that would respond to a motion of pendulum rotating, not oscillating, but rotating. And in any case, these periods are the periods of this essential Galois elliptic function, uh, and being elliptic angles of the first kind are most efficiently calculated via that remarkable method that Gauss discovered on May 30th, 1799. And in fact, signified a new era of analysis, which we now are coming closer to understand the impact of. So now, let me, of course, go on here to tell you what that elliptic angle of the third kind is, the one that was indicated as appearing in rigid body motion. So here is a page from Arnold's very well-known book, which is called Mathematical Methods of Classical Mechanics. It's translated to many languages, English in particular. So this is a translation. Here the translator remark about the invariable plane. This is the plane that appears in Poinsot's the construction, where the ellipsoid of inertia rolls without slipping. And so the Arnold is presenting this angle here geometrically via this Poinsot construction. So this is one way to consider this angle, which in fact turns out to be an angle that would correspond to a complete elliptic angle of the third kind. So let me show you how we might calculate it. So in fact, actually, here is something rather significant, because I'm presenting to you here a formula for the rate of precession, which is symmetric in the moments of inertia, principal moments of inertia, ABC. I mean, these small letters A, B, and C somehow are corresponding to these capital letters ABC. Actually, this formula is also given in this abstract of my talk, so you might see it more explicitly there. Well, y is a function of the squares of the angular speed, momentum, and energy. Well, r shear is twice the energy. So anyway, this formula for precession, or the rate of precession, is symmetric in the principal moments of inertia. However, when you integrate it, then you no longer have that symmetry in the moments of inertia. I mean, it's important that the integrand is symmetric, but not the integral itself. So once you integrate, this is an elliptical integral of the third kind. And again, due to these efficient methods, which were generated by Gauss' remarkable discovery, then we might now here's an explicit calculation of this angle. Now you see here you have two summands here corresponding to these two summands here in the rate of precession, you know, and there is some very important crucial special case which you might call the critical motion of a rigid body would correspond to this letter B, which is corresponding in turn to the middle moment of inertia. When B vanishes, then you have this integrand vanishing, but the integral now is being t here is approaching infinity. So somehow, although this integrand is approaching zero, we attain an improper integral which has some finite value. And this is actually some quite remarkable an elliptic integral, which is as a critical case of this elliptic integral of third kind, because it has very neat geometrical three space geometrical interpretation. So let me show you what exactly the integral I'm talking about. So it can be presented in this way. You know, you have this integral here, which we might explicitly calculate, and then you have this x, this upper limit approach infinity. Uh, um, so then we would define this way an integral which would be dependent upon three moments of inertia. Uh, um, so and then these moments of inertia can be ordered in ascending or descending order, and some quite interesting things are happening here. So I wrote this explicitly, some explicit calculations for the value of the integral for values 278 and 872, ordered in reverse. Whatever these ABC and CBA, this difference would always be pi over 2. Uh, Now, so let me just maybe before I give you another clearer geometric interpretation of what's going on, show you the same slide, maybe in Russian here, again about this same issue. Now, let me point out again that this is an improper integral, which we are calculating, and we are paying attention to this distinct ordering, ascending and descending. So now here let's go on to this picture. So this picture is from Shaban Jenkins' Ethical Mechanics of Space Systems. I think now the fourth edition is presented. I don't know whether that picture is corrected. So let me show you what I mean here. So these are the curves here. This is the rigid body frame of reference. So we have this frame attached to this rigid body, and in this frame you have these curves, which are the curves which trace the angular momentum in the from the body's view frame. So what you have to pay attention to is that these curves here are oriented outwards, whereas the curves here are oriented inwards. So somehow this separating curve here serves as a mirror, you know, with one orientation here being reversed with the orientation here. But then take a look at what's happening. So what would be the orientation of this curve, separating curve here. So let's say it's going on this way, and so this is another one is coming towards it. But then wait, I mean you have other curves also. So this is, looks like a sink, and there is no source. But this is a point corresponding to the so-called unstable equilibrium. So you cannot have this situation going on. So actually, that prompted Victor Sazonov, who was present at that talk, which I mentioned on January 31st, to ask, why are you presenting us the wrong picture? Well, I mean, so he meant that we might really correct it. So we might go here, and then we might go here the other way, and then we also might go here the other way. So you have then two in and two out. Uh, so, I mean, I must mention that in Landau Lifshitz, these curves were not oriented. So the authors must be really praised for doing some brave work of giving orientation to these curves. Uh, but then, so if we do so, so we have this curve coming in and this coming out. But then we would wonder, why would this be coming in and this is coming out? Can we have this converse? In other words, what would happen with the mirror image of this picture? Or in other words, if you have a rigid body moving, what about its mirror image? Now, or in other words, you have the so-called Euler equations, which describing the motion of the rigid body. And very often, people who are concerned with applications, they very often are geared towards using the so-called right-hand rule. But then, in the mirror, the right hand is now left hand. So the question is, what happens to this right-hand rule in the mirror? The question of mirror symmetry is something actually prompted some of my colleagues to tell me that they would have to think about this, but mm, uh, I'd say many of them never came back to me in spite of that promise, which was made years ago. Um, so here's the picture now with this. Mm, mm, Let me show this somehow. A slide is stuck. Now it's unstuck. So here is some right-handed system here on the left, IJK, and its mirror image is a left-handed system. And so if you have an orientation here going this way and then coming back this way, the mirror image would have the reverse orientation. So there is this duality here that we really somehow have to be really careful about. It's something very relevant to practical applications. Alexander Siliverstov, who made this accessible to a wide range. So I hope this would enter physics and mechanics textbooks. This is a nice review, a historical review of conic sections and their generalized axis of symmetry, which really, for very good reasons, called the Galois axis. Actually, it has, because it's exactly the case of that critical case, which I shown you when that formula symmetric in the moments of inertia appears with that second summand vanishing, but yet the integral of it is not. So actually, this is the case of uniform rotation of Galois axis. Let me show you now, maybe in a neat way that's being done. Many thanks to the team of mathematical modeling. Simple pendulum exhibit that triple solution at that unstable equilibrium. So this is exactly where the pendulum is embedded. So we have this uniform rotation, and the middle axis make that pendulum motion. Remember when I told you about the square, I said I promised to come back to this, because this would be the square root of that pendulum critical motion. So this half circle motion is exactly the square root of that pendulum critical motion. And of course, you have two square roots. So that's why you have two solutions here corresponding to one Galois axis. So this is the same rotation. And you have, uh, again, three solutions if you have another rotation, say counterclockwise. So this triple motion is in fact, as Alex Madanov noticed, is really analogous to the simple pendulum. Uh, Maybe this will be the last presentation I show you, and only in case if it loads. So this is just uh, two uh, other um, flips. Uh, and as I told you, these flips are when you end up uh, so the major and the minor axis are not returning to the same position. They would be changed by an angle, which that was calculated with that improper integral. So that improper integral is indeed, as I promised, has this neat geometric interpretation. So that's it for my talk. And I'm thankful to the organizers for giving me an opportunity to present this talk.